Longer than all of you have been alive. This is my 29th year teaching at Front Range Community College in the math department. And I've taught Calc 2 a bazillion times. So ask me anything about Calc 2 stuff that you aren't understanding, and I will try to help you. Today, we're going to talk about, how's it going? Alternating series. So up until this moment, the series you've been analyzing have been series that have all positive numbers. And we've got this wild thing in our mind that you can add an infinite collection of positive numbers and get a finite answer. Right? That's what infinite series are all about. Does that make sense to everyone? That's what an infinite series is. In general, up to this point, you've got positive numbers, an infinite collection of them. You add them all together and you get a finite number. It's possible that it's infinite, but the ones that are interesting are the ones that actually are finite. And so in your mind, when you're thinking of an infinite series, what I would like you to be thinking about is a common rational number that you are very familiar with, something like 1/3. Right? That is an infinite series right there. This is 0.3 plus 0.03 plus 0.003 plus etc. And that example makes it crystal clear that you can add an infinite collection of positive numbers and get something that's finite. Right? So that is the example that you want in your mind. And the key feature is that the only way this infinite series can converge is if these numbers that you're adding get tinier and tinier to the point that they don't matter. You can think of it kind of like blowing up a balloon. If you keep putting in a lot of air, eventually it's going to explode. But if you put in smaller and smaller and smaller and smaller amounts until you're putting in just insignificant amounts, you can just blow the balloon up and it won't explode. So those are the good images to have when you're thinking about an infinite series. So now today, we're going to throw in this wrinkle, and we're going to put some minus signs in here. And we're going to be really deliberate, and we're going to put a minus every other term. In the sections that follow 10.6, 10.7, and 10.8, you can talk about a series that has a sprinkling of minuses, but not necessarily so systematic that it's every other term that's negative. So for us, in this section, we are very precise. Every other term is negative. Every other term is positive. So it has to be every other term if we're going to call it alternating. Now, you've already talked about the harmonic series. The harmonic series, all positive terms, and it's a threshold series. This is our threshold P series. If the power on k is 1, it diverges. And that's the harmonic. You showed it with the integral test. If the power on k is bigger than 1, what will happen? Convergent P series if P is bigger than 1. The power, P stands for power. If that power is bigger than 1, you get convergence. So now we're taking this divergent series and we're saying, hey, let's modify it a little bit. Let's turn every other term negative and see what happens. Okay, so to force every other term to be negative, we introduce this factor up here that's called a switch. It's either going to be -1 to the k or -1 to the k plus 1. Depends on the situation. And then the question is, well, does that converge? So if we think about the balloon scenario, we're putting in air, but then we're letting a little air out with the negative sign. Putting more air in, letting a little air out. And the question is, will that converge or not? And it turns out that the alternating harmonic, if we look at the sequence of partial sums, which is how you analyze an infinite series, you always are looking at the sequence of partial sums. That's how we attack an infinite series. So we have two things happening. We have our sequence of terms, and then we have our sequence of partial sums. Two totally different things. Like these right here are the sequence of terms, and the sequence of terms have to go to 0 in order to get convergence. They must go to 0, but that's not enough. They have to go to 0, and they have to go to 0 fast. So when we look at that harmonic, those are going to 0. They're just not going to 0 fast enough So that diverges. All right, so now when we go and look at the sequence of partial sums here, and let me just make sure it's clear, sequence of partial sums. With this example I have on the board, the sequence of partial sums is 0.3 and then 0.33 and then 0.333, etc. And so that sequence of partial sums, if it has a limit, that is the sum of the series. And if that sequence of partial sums doesn't have a limit, we say the series will diverge. So let's look here, alternating harmonic. The red is the sequence of terms. So +1, and then minus 1/2, and then plus a third, minus a fourth, plus a fifth, etc. So the red is the sequence of terms. To get to the partial sums, the first partial sum is the same as the first term. The second partial sum is this dot here. So 1 minus a half will put us at 1/2. And then we add a third, subtract a fourth, add a fifth, subtract a sixth, etc. And what you can see from this graph is that the sequence of partial sums does have a limit. The limit turns out to be natural log of 2, which we can't show you in this class. You have to go to an advanced calc class to see that. But that's what it does converge to. So the alternating harmonic equals natural log of 2. So it converges to natural log of 2. All right, so what that means is putting the minuses in here turns this alternating series into a convergent series. And this idea leads us to the alternating series test. So here is our sequence of partial sums. I've graphed them for you. It's a little harder to see that these numbers here are converging to natural log of 2. When we graph it there, it's a lot more obvious that we keep oscillating around this line, and that line happens to be natural log of 2. So there is our conclusion with the alternating harmonic. So the alternating harmonic is a really important one to have in your mind because it's going to be so different than the harmonic. Harmonic diverges, but the alternating harmonic converges. And so the question is, okay, well then, what is our generalization here? And the generalization is the AST, the alternating series test. So when we have an alternating series, we always use the alternating series test. So this is a special series. I'm going to jump out to the last slide in chapter 10 for a second. When we look at a series, if we were just given a series and we want to analyze, does it converge, does it diverge? The question is, well, how do I attack it? And so up to this point, the alternating series test is your 8th test or type of series. And this last slide here kind of lists the order of things. And so we have four what I call special series. That they're not really, the 3 of them aren't really tests. Right? You have a geometric series and you analyze, oh, if the common ratio is less than 1 in magnitude, it converges, otherwise it diverges. You have a telescoping series, P series, and then an alternating series. So these are our 4 special series. Divergence test, that says if the limit of the terms is not 0, it instantly diverges. Divergence test can only find divergence, it can't find convergence. And basically the divergence test is giving you divergence for really egregiously diverging series. Like if we look at this series here, many students get confused by that and they say, oh, there's no k there, so it probably converges. But we have to remember what this notation means. This means 1 plus 1 plus 1 forever. So does that series diverge or converge? If you add 1 to itself an infinite number of times, that's diverging. That does not converge to a number. So that's going to diverge. We would say it's infinite or it diverges. So this is egregious. These terms are not going to 0. And the divergence test can only pick up that egregious divergence. If you have a series that the terms aren't even going to 0, there's no chance it converges. It has to diverge. Unlike the harmonic, the harmonic, these terms are going to 0, so the divergence test is inconclusive. The terms are going to 0, do more work. If the terms are going to 0, it might converge or it might diverge. So the divergence test is always our first kind of consideration. And then if we have a special series, we do whatever that special series tells us to do. And then you've got your other ones down here, your integral test. And then in 10.7, you'll do the ratio and the root test. And the comparison test you should have done last week. So that's kind of the bigger picture where we're at. The alternating series is our last special series. So we have to be clear on a couple things with alternating series. The first is the way they're written. The a sub k does not include the minus. So we think of the minus as separate from a sub k. So when we write 1 minus 1/2, a sub 2 is 1/2. The minus is coming from this thing that we call the switch. So the a sub k is positive. Okay? So we have to make sure that that's clear. The AST has 2 steps. The first one is the divergence theorem, divergence test. Right? You take the limit of a sub k. If the limit of a sub k is not 0, the series diverges. Because if you add something that's not going to 0 an infinite number of times, that's divergence. Right? If the limit is 0.1, if you add 0.1 to itself forever, that diverges. That's not finite. So the divergence test is actually the first step of the alternating series test. So we want to take that limit. If it's not 0, we're done. The series diverges. The second thing is that we need to show that the terms, and by terms I mean the positive pieces. We're not looking at the negative ones. The terms of a sub k, they're all positive. We need to show that they're decreasing. So if the limit is 0 and the terms are decreasing, then the series converges. It's remarkably simple. All you need to know is that the limit is 0 and the terms are shrinking. If that's true, then the series, alternating series, converges. If the terms are going to 0 in a monotonic way, there's no oscillation. They're just going to 0. So if the limit is 0 and the terms are decreasing, that's it. You have convergence. So for the alternating harmonic, there's the alternating harmonic. A sub k does not include the switch. A sub k is just 1 over k. Limit of 1 over k, 0. So that means the divergence test is inconclusive. We have to dig deeper. So divergence test is inconclusive. All we need to know now is that the terms are getting smaller. So the next term is smaller than the prior term. If that's true, all the way through, then the alternating series will converge. So to show with 1 over k, that's what we want to show, WTS, want to show. We want to show that a sub k is bigger than a sub k plus 1. A sub k plus 1, we just put in a k plus 1 for the k. So we don't know, is this true or not? We're trying to prove it. We cross multiply. Multiply both sides by k plus 1 is going to move the k plus 1 to the left. Multiply both sides by k moves the k to the right. We can subtract off k and we get to an inequality that we can solve by inspection. That inequality is true. We are done. The limit is 0. Terms are decreasing. Therefore, it converges. So that's it. Alternating series test. 2 steps. That's it. Any part of that you're not sure about? Any part of it that's not making sense? In a lot of ways, it's much simpler than series that have positive numbers only. Like you have the p series, and you can just look at the denominator, and you have to decide on the k, the power on the k, and you have to do a little more analysis. For alternating series, it's a little bit simpler. As long as the terms are going to 0 in a decreasing manner, converges. So you should instantly be able to look at this and tell me that it converges. It shouldn't take more than 3 seconds. Because you look at this, the a sub k is 1 divided by square root of k. All right, the k is in the denominator, and as k gets bigger, the denominator gets bigger, so the fractions go to 0. Right? And when there's only a k in the denominator, if you add 1 to the k, that increases the denominator, which shrinks the fraction. So it has to be doing this, has to be ski slope. Right? So the terms are going to 0. There's never any oscillation because as k gets bigger, the denominator gets bigger, which means the fractions get smaller. So limit is 0, and it's decreasing. So the math in the infinite series chapter should be more about confirming what you intuitively know to be true. So we can look at that and intuitively argue that that does converge. We haven't done the math yet, but the math should be confirming that. So let's go through the 2 steps. So we want to take the limit of a sub k as k goes to infinity. Well, a sub k in this case, again, it's an alternating series. So we just ignore the switch. That part is a sub k. Now, one thing I do, once I've established that the limit is as k goes to infinity, I'm not going to write it every single time. We've already established that k is going to infinity. So I will not write it every single time. And as k goes to infinity, this denominator blows up, so the fractions shrink to 0. So that limit is 0. Check. First step, done. Second step, we want to show, bless you, that the terms are getting smaller as you go out in the series. So that's what we want to show. We want to show that the next term is smaller than the prior term. That's what we're trying to show. And again, we don't include the switch. So a sub k is 1 over root k. And we don't know. I'll put a little question mark there because I don't know if it's true. In my heart of hearts, I know it's true, but we haven't proven it yet. So that's what we want to show. If we do our cross multiplication, we end up with this inequality. So multiply both sides by root k, moves the root k up here. Multiply both sides by root k plus 1, moves it over there. Everything is positive. You don't have to worry about switching the inequality symbol. Multiplying by positives doesn't change the inequality symbol. So we are here. We can almost always get down to a numerical inequality. So here I'm going to square both sides. And then I'll subtract k from both sides. And we get down to a numeric inequality we can solve by inspection. This is true. Therefore, this checks. We've now checked step 1, checked step 2. Our conclusion, convergence. That's our conclusion. So therefore, we have convergence using the alternating series test. So that's how the alternating series test works. 2 steps. Limit, and then decreasing. Any part of that you have a question on? All right. So let's go to this one, top up there. That may not look like an alternating series. May not look like an alternating series, but it is. If you think about that numerator, cosine of pi k, if you plug in a k value that is even, you're taking the cosine of 2 pi. Oh, did I say that right? Yeah. If you plug in an even number, cosine of 2 pi or 4 pi or 6 pi, what's cosine of 2 pi? 1. We're on the right edge of the unit circle, cosine of 2 pi. And if we're thinking about going around the unit circle, 2 pi puts us there, 4 pi puts us there, 6 pi puts us there, et cetera, et cetera. So anytime we plug in an even value for k, we're on the right edge, so cosine's plus 1. Anytime we put in an odd k, so pi, 3 pi, 5 pi, 7 pi, we're going to be on the right, this edge left edge of the unit circle over here. And that value is -1 for cosine. So this is just an alternating series. Does it converge? So think in your mind, do the terms go to 0? As k goes to infinity, do the terms go to 0? Yes. Because the denominator is getting bigger, right? The denominator is getting bigger, so the fractions are shrinking to 0. And that second step then is, are they decreasing? We ignore the switch, the 1 over k squared. Does 1 over k squared go to 0 in a decreasing way? Yeah. Right? 1 over k squared looks just like 1 over k, looks just like 1 over k cubed, just like 1 over k to any power that's bigger than 1. So we know that this is going to converge then through that discussion, but that's not the math. Let's do the math. So step 1, the limit as k goes to infinity of a sub k. Again, a sub k does not include the switch, so this is the limit of 1 over k squared as k goes to infinity, and that's 0. So that checks. So that tells us now go to step 2. We now know that the divergence test is inconclusive. The series could converge. Step 2, we want to show that the terms are getting smaller as you go out into the series. So we want to show that. So a sub k is 1 over k squared. We want to show that 1 over k plus 1 squared is smaller. So we're trying to show that. We put a question mark because we don't know. That's what we're trying to prove. We do our cross multiplication. If we cross multiply, or multiply by the least common multiple, whatever your vocabulary happens to be, clear the fraction one way or another. Now we take the square root of both sides. Everything is positive. If everything is positive, you can take square roots, you can square, you can take cubed roots, whatever. You can do all this stuff without affecting the inequality symbol. And then we can ditch the k, subtract k. We get 1 greater than 0. Yeah, that's true. So now that checks. So now we have both steps. Limit is 0. Terms are decreasing. Series converges. So therefore, converge. All right. Just want to look at the next page. Both of those are a little bit, yeah, that's. Why don't you all start this one, and let's see how far you get, and then we'll do it together. But so start this one. Intuitively, we should know that it converges because all the k's are in the denominator, and as k goes to infinity, the fractions are going to 0. So it's going to converge. So try to show step 1 and step 2. At least get through step 1. Step 2 is going to be a little trickier with that natural log. A little bit trickier. You may or may not get stuck on it. Let me know if you're stymied on any of it, and I can nudge you in the right direction. Did anyone have trouble with step 1? Pretty straightforward, step 1. Notice the notation. Traditional notation, when you square a natural log, is to write it the way I wrote it there. This book uses this kind of trigonometry format for squaring the function, which is not, you won't see that in every book. A lot of books still use the more traditional thing and reserve this notation only for trig functions, but you can write it either way. It's totally fine. And that limit is 0. Denominators go into infinity. Numerator is constant. Fractions go to 0. So step 2 is the one where some of you might get a little snagged on it. Let's go through it. So we want to show that the terms are getting smaller as we go out into the series. So we would like to show, let's see, a sub k is that. A sub k plus 1. A sub k plus 1, we replace each of the k's with k plus 1. So that's what we want to show. Now, what we did with the other ones was clear the fractions. Clearing the fractions in this case isn't going to be quite as helpful. So here is my suggestion. Let's put the natural log factors on one side and the other factors on the other side. And then let's see if we can analyze this. So I'm going to put the k plus 1 to the left. So we have that. And then I'm going to multiply both sides by natural log squared of k, so I can put that up here on the right. So we have that. And then on the right, I'm going to do one more thing before we analyze it. I see that both the numerator and denominator are squared. So we could pull that square out and write this as natural log of k divided by natural log of k plus 1. And then that entire quantity is squared. OK. So let's see if we can analyze this here. When you look at the left-hand side, is it obvious to you that the left-hand side is always bigger than 1? Because the numerator is bigger than the denominator, so that fraction value is always bigger than 1. Correct? So that's always bigger than 1, so I'll put that indicator down here that that's always bigger than 1. Now let's look at the right-hand side. Let's come in here. What is true about the right-hand side? It's always less than 1. Do you agree? So this side is greater than 1. This side is less than 1. Right? Because the natural log function is a continuous function that's increasing. If we were to graph the natural log function, we are all very familiar with the natural log function. Looks like that, passes through 1. If your k is here, your k plus 1 is out here, and that distance there is bigger than that distance. So natural log of k plus 1 is greater than natural log of k. So that right-hand side inside the parentheses is always less than 1. And if you square a number less than 1, what happens? Gets even smaller, right? So we square this, and the whole right-hand side is less than 1. It's even more less than 1. So the left-hand side is always greater than 1. The left-hand side is greater than 1. Right-hand side is less than 1. So is the inequality true? Yeah. Yeah. On this side, we have less than 1. On this side, we have greater than 1. Therefore, it is true. So this is true. That checks. So now we have both steps checking. So therefore, we have convergence, because both steps checked out. So 2 steps to the alternating series. Test. alternating series test. Okay. This one, let's go through this together. This one's a little bit weirder. So you saw in recent days these more abstract functions. We have the k factorial function, which, if you recall k factorial, remember that k factorial is repeated multiplication by factors that are shrinking by 1 unit, all the way down to 3 times 2 times 1. And that's k factorial. Everyone okay with that? All right, we've seen that. And what about if I did this? What about if I wrote k plus 1 factorial? K plus 1 factorial, that's going to be k plus 1. What's the next factor?
Just k factorial.
Just k factorial, exactly. So if we subtract 1, we get k, and we could just write that as k factorial. Like, for example, if we had 6 factorial, we could write that as 6 times 5 factorial, or 6 times 5 times 4 factorial. Right? We have a lot of choices. Right, so that's going to help us here in the long run, is just understanding how we can sort of deal with those things. Now, the denominator is the power tower, k to the k. If you graph it in Desmos, x to the x, it's a wild-looking, crazy thing. We call it a power tower. It grows much faster than the factorial grows. The factorial is going to grow faster than an exponential. The power tower is going to grow even faster than a factorial, way faster than an exponential or a polynomial. We can't do the limit of this in your traditional way. Your traditional way, when you're doing this limit, is to use some sort of clever math to mathematically compute the limit, and we can't do that here. We can't use L'Hopital's rule. We don't know how to differentiate a factorial function. We don't know how to differentiate a power tower, so we can't use L'Hopital's rule. All we can do is say that this is going to be 0 by growth rates, because the power tower grows so much faster than the factorial. In the book, they do this kind of notation here with 2 greater than symbols. Just means that the power tower grows significantly faster than the factorial. So all we can do is use growth rates. We can't do any L'Hopital yet, and something like that. So again, the first step is the divergence test. That checks. If you get 0, that means the divergence test is inconclusive. We don't know. The series could converge or could diverge. We don't know yet. So we dig deeper. Now we want to show that the series of the a sub k's are decreasing. So the magnitude of the terms are decreasing. If you sort of think about including the minus sign, the magnitude of these are decreasing. So let's see if we can show that. So we have k factorial over k to the k. We don't know, is that going to be less than, is this going to be less? So here we have to replace all the k's with k plus 1. So that's what we would need to analyze. We need to figure out if that's true or not. Once again, it will be helpful to combine like the factorial terms and combine the other ones. So there's a couple of ways we could do this. We could put all the factorials on the left. We could put all the powers on the right, or vice versa. It doesn't really matter. But let's just group them separately one way or the other. So my inclination is going to be to write this as k factorial over k plus 1 factorial. So dividing both sides by k plus 1 factorial, and then multiplying both sides by k to the k will give us this situation. And as we're doing this, I'm going to take this moment to do a little bit of reduction with this denominator on the right. Everybody agree that k plus 1 to the k plus 1, we can use the laws of exponents and break that apart into k plus 1 to the 1 and k plus 1 to the k. If you multiply those together, you add the exponents and you get back to there. Bless you. So we have that. Now let's look at the left-hand side for a minute. The left-hand side, we can rewrite that denominator as k plus 1 times k factorial. And on the right-hand side, I see two powers of k that can now be combined into one thing. So I'm going to rewrite this as, I'll write the 1 over k plus 1 multiplied by k over k plus 1 quantity raised to that k power. So we've got that. All right. On the left-hand side, k factorials cancel. We also have a k plus 1 in each denominator. So if we were to multiply both sides by k plus 1, those k plus 1s are going to cancel. So we can also cancel this k plus 1 and this k plus 1. Multiplying both sides by k plus 1, those two k plus 1s are in the denominators. So let's write down where we're at. So on the left side, we now have 1. And then on the right-hand side, we have k over k plus 1 to the k. K is a positive number. We can take the kth root of both sides. And if we take the kth root of both sides, we get that. And you can probably already see that it's true. If we can go down to a numerical inequality, we usually do just to be complete. So multiply both sides by the k plus 1 to clear the fraction, subtract the k. And we get down to this numerical inequality, which we can solve by inspection. That's true. So now we have a check on both steps. So our conclusion is, therefore, we have convergence. Therefore, that series is going to converge. All right, anything mysterious about those steps? Any part of that you want some extra clarification on? Does it seem logical enough? Okay, let's talk about the remainder. So, as you know, when we analyze an infinite series, the way we decide on convergence or divergence is to look at the sequence of partial sums. The sequence of partial sums. So in your mind, let me see if I have access to that slide. I think I put it in here. I have a visual. This is the picture in your mind of a convergent series. This is what you should be visualizing. Every time you imagine a convergent series, here is the sequence of terms. A sub 1 is the purple, the A's are the purple, so A sub 1, A sub 2, A sub 3, etc. So those are the sequence of terms. The black dots are the sequence of partial sums. So if a series converges, it's like a horizontal asymptote. The sequence of partial sums has a horizontal asymptote or a limit. And so that's what you should be visualizing. As the terms go to 0, if they go to 0 fast enough, the sequence of partial sums will have a horizontal asymptote, and the series will have a sum that will be finite. Right, so that's the picture in your head. The terms going to 0, the partial sums with a limit, whatever it happens to be. Okay, so whenever we are attacking an infinite series, you should have a visualization of the terms and a visualization of the sequence of partial sums. So that is our image. Come on, close. We are in here. So now let's talk about the remainder for an alternating series. You should have talked about the remainder of a series already a little bit. In Calc 2, we usually don't get into the weeds too much with remainders. The remainder for an alternating series, I want to go up here and look. Is that there? So you should have seen, I don't know where I would have it in here. It doesn't matter. I'll just use words, no picture. So you should have seen an integral that can be used to approximate the remainder. When we think of an infinite series that converges, the sum of the series is broken into two pieces. It's broken into the partial sums, S sub n, and then whatever is left is called the remainder. So if our series converges, you can think of the leading terms being S sub n and then the tail being R sub n. So for example, when we write out the sum of the series, we're adding up all these terms. We'll get to a sub n. The sum of the first n terms is S sub n. And then we have the rest out here. So the leading terms up to the nth term, that's S sub n. And then R sub n is the sum of the tail. Right. So understanding how small the remainder is very important. If you're dealing with manufacturing and you're looking at tolerances of some machining process, there's different tolerances that tell you how accurate you need your machining to be. The more accurate you are, the more money it costs. So we want to figure out the minimum number of terms necessary to meet whatever the legal or manufacturing threshold is. And we don't want to add extra terms because that adds extra money to our manufacturing process. So we need to have an idea of how to deal with this remainder. And a previous class should have given you a crazy integral inequality where the remainder is bigger than some integral and smaller than another integral, and they're kind of nasty to deal with. If you go on in math and engineering, you will take classes like numerical analysis where you spend a ton of time dealing with remainders, and there's a whole slew of techniques to analyze a remainder for an infinite series. In this class, we're just going to focus on the remainder for the alternating series because it gives you the idea, but it's not super complicated. So let's take a look at this statement right here and focus right there. So we have our sum. Our convergent alternating series is broken into the leading terms, S sub n. The trailing terms, or the tail, R sub n. That is the remainder estimation right there. All we do is look at the first unused term. That's what that says. Let's put it in words for a second so that you can kind of get a better idea. So if we look at the alternating harmonic looks like this. It goes on forever, and it equals natural log of 2. So S sub 2 is that. S sub 3 is that. Etc. The S sub 3 is the sum of the first 3, S sub 4 is the sum of the first 4. What this means is the following. S sub 2 is within the first unused term for S sub 2 is the 1/3. That's the first unused term. So this tells us that S sub 2 is within 1/3 of the sum of the series, which is natural log of 2. It tells us that S sub 3 is within how much of ln2? If we add the first 3 terms up, 1/4 is the first unused term. That is going to tell us how close we are to natural log of 2, to the actual sum of the series, etc. So all we have to do is look at the first unused term, and that's going to give us a pretty good idea of the size of the remainder. OK, so let's look at a visual now. With an alternating series that converges to S, the partial sums are going to oscillate around that asymptote. And if we think about this, so I've chosen an S sub n that's up here right now. It's more than the sum of the series. Sum of the series is down below. The next term would be negative. It would take us all the way down to here. There's S sub n plus 1 right there. Do you see that the remainder is the actual difference between S sub n and the sum of the series? Right? It's the distance between S sub n and the sum of the series. It's the distance between S and S sub n. That is the exact remainder. Most of the time we cannot find that. It's very rare that we know the actual sum of a series. Very, very, very rare that we know that. There is the remainder. And if you look at a sub n plus 1, it takes you all the way down to here. Clearly, the green line is bigger than the black line. So the remainder is less than the next term, the first unused term. If we go to S sub n plus 1, so we add or subtract, add a negative, whatever you want to think of it, however you want to think of it. Now we're down here at S sub n plus 1. To get to the next partial sum, we're going to add a sub n plus 2. That will take us up to here. And once again, we see that, oh gosh, this is the actual remainder right there. And this green line is bigger than that remainder. So this is going to be our simple method of approximating the remainder. And as we go further and further out, the idea persists. So that's what this is doing. If we look at S sub 4, no, let's pick a random one. S sub 11 is within how much of ln2? 1/12. Yep. We're going to be within 1/12. The next term we're going to add is a sub 12. A sub 12 is going to be 1/12. That's the next term we're going to add. So that's the first unused term for that partial sum. So alternating series have this cool little feature that you just look at the next term, and that's going to be your gauge on the error. Not super complicated. Way easier than those two integrals that bound our remainder. So this is the one remainder process that we are going to look at in depth in this class. And so here's a picture of our expanded series. There's a picture of S sub n right there. And S is approximately equal to S sub n. The remainder is going to be the first unused term. All right, so now let's do some harder math. So this says determine how many terms of the following convergent series is alternating. Convergent alternating series must be summed to have a remainder less than 10 to the negative 4. So here is how I will attack this. In my math lab, they use a slightly different philosophy, but they are the same. And you can use either one, depending on which one feels like it makes more sense to you. So here's what I'm going to say to myself. I want to know the first term that has a magnitude less than 10 to the negative 4. If I can find the first term that has a magnitude less than 10 to the negative 4, I add up everything in front of that term. Because that term is then going to be the remainder estimate for everything in front of it added together. So that's the philosophy I'm using. Find the first term that's less than 10 to the negative 4, add up everything in front of it. Seem reasonable? So, I want to know when is this a sub k less than 10 to the negative 4. Let's write that as a fraction. So if we write 10 to the negative 4 as a fraction, we have that. So I'm looking for the smallest k that satisfies that inequality. Cross multiply. What is the smallest k? K, remember, is positive integer. Smallest k that satisfies that? 10,001, right? Just add 1. This will be the smallest k. All right. Now let's visualize our expanded series. So this series starts at 1. So I'm going to call the first term a sub 1. And do you agree that that term should be positive when we plug in k equals 1? K equals 1 is going to make an even exponent on the negative 1. So negative 1 to an even is positive 1. The next term will have a negative in front of it. The next term will have a positive in front of it, etc. OK. And now I'm focusing on this k, 10,001. I'm going to go one term before it, which is a sub 10,000. And then I'm going to have an a sub 10,001. And then I'm going to go one term after it for good measure. OK. So can you tell me, should this be plus, minus, plus, or should it be minus, plus, minus?
Plus, minus.
Say again?
Minus, plus, minus.
Minus, plus, minus. Why? Why is this one negative?
That one would be odd if you had 1.
So if we look down here at the index, it should match the same sign as the other even subscripts. It's going to have exactly what you said, a negative. It's going to end up with an odd number up here. So that's negative, that's positive, that's negative, that's positive, goes on forever. So there's where we're at. This term, when k is 1001, 10,001, this term is our first term that's less than 10 to the negative 4. All right, so that's our remainder term. That's going to be our remainder term if we add up everything in front. So we want to add up all of these. How many terms is that? 10,000. Right? We're starting our counting at 1, not 0 or some other strange k value. If we start our counting at 1, first term, second term is 2 terms, 3 terms, 10,000 terms. So this is how many terms we have to add up. 10,000 terms need to be summed. All right. So this is S sub 10,000. If you add the first 10,000 terms together, that is called S sub 10,000. So S sub 10,000, and all it asked for was the number of terms, but for completeness, I'm just going to write it like that. Write it in our summation notation. So S sub 10,000 looks like that. And this is within 10 to the negative 4 of the sum of the series. Usually you don't know it. In this case, they happen to pick a series that we do know the sum. So we will be within 1/10,000th of ln2. So let's try another one of those, and we'll take our break. So, same idea here. We want to know how many terms need to be added together to be within 1/10,000th of pi over 4. So we look at our a sub k. That's 1 over 2k plus 1. And I'm curious, what is the k value, the lowest k value that satisfies that? So we cross multiply. We subtract 1, we get 9,999. And divide by 2, we can do that in one fell swoop. We're good. So now we want the first k value that satisfies that. What will the first k value be, the first positive integer that will satisfy that? This is going to be a skosh under 5,000. So 5,000 will be the first k value that satisfies this. Now that does not mean that we necessarily have 5,000 terms. We have to look at our indexing to see how many terms this is going to correlate to. Like this one up here, we got our k value to be 10,001. We had 10,000 terms. So let's see. Well, let's do the same thing we did up there. We're imagining expanding our series. First term here is a sub 0. And will that be a positive in front of it, or will it be a negative in front of it? Positive. So we plug into 0 as an exponent. That's an even number. Even number on a negative 1 is going to give us positive. So we're going to have this sequencing. So we'll have that sequencing. So now let's get down in the neighborhood of k equals 5,000. Let's go a term before it and a term after it. Let me just lower this a little so I have a little bit more space. So we're going to have an a sub 4,999. We're going to have an a sub 5,000. We're going to have an a sub 5,001, and then etc. So now we just have to decide, should it be minus plus minus or plus minus plus? And we look, and the evens all have a positive in front of them. So it's going to be minus, plus, etc. All right. And then we found that when k is 5,000, we are right here. So this term is going to be the first term that is less than 10 to the negative 4. So that is our remainder term. That's the remainder for when we add everything up in front of it. So we're going to add all of those. And how many terms is that? 5,000. Right, because we started at 0. If you start at 0, 0, 1, 2, 3, 4, right, that's 5. 5 fingers if you start at 0. So we have to add 1 to this final subscript here, so this will be 5,000 terms. And that was what the question asked us. And if we wanted to, we could write this as S sub 5,000. So S sub 5,000, you could write that summation notation if you wanted. So S sub 5,000 is within. So visually, you're sort of visualizing, okay, I've got the sum of the series. I've got this set of leading terms. We're going to be within 10 to the negative 4 of S, the sum of the series, which we happen to know in this case, which again is very, very rare. So we'll be within 10 to the negative 4 of pi over 4. So logical. Oh gosh, we love math. All right, let's go ahead and take a 10-minute break. And then we'll do some more alternating series. Come on, where are you? Hopefully it'll be great next year. You would think they would charge less for next year's pass because this year was such trash. But no, they raised the price anyway because we're thinking that it can't happen again. So they want our money. Yes. Okay, so another alternating series here. Same scenario. I want you all to try this. So try to give this one a good go. We want to know how many terms do we add together to be within 10 to the negative 4 of the sum of the series. So see if you can you can look at the prior example and try to use that as a model to see if you can figure out the number of terms. We've done 3 examples. Let's see if you can piece it together.
No. It was not even 24 hours, man.
You said from 6 a.m. to 6 a.m.
I was done. I tapped out at like 12.
You guys study for 24 hours?
Yeah.
So good.
We'll probably an hour.
Flying. 1 problem an hour.
Easy, right?
Easy.
That's what I'm thought.
Sometimes you just gotta lock in. 1 problem an hour. Hopefully the pay is good. Did you take the square root of 10,000 in your head? Beast mode. So what do you all get for K? 101? All right, that's the easy part. We got 101. All right, so, and you might have noticed the pattern already if this starts at 1, what that K value means in terms of the terms. But we will write out a visual representation of the expansion. So the first term is going to be called a sub 1, the next term a sub 2, a sub 3. And should that go plus minus plus or minus plus minus? So it should start with a plus. Yeah, when we plug in a 1, we get an even on the negative, so that's going to give us a plus. And so we'll alternate in this way. And then I'm just going to grab a few terms in the middle that surround this. So A sub 100, A sub 101, A sub 102. And if we look over here, we see the even index corresponds to a negative, so it's going to be negative, and then positive, and then our dots are et cetera. So this term right here, when k is 101, this is where we're at, and that term is less than 10 to the negative 4. So that's acting as the estimate for the remainder if you add everything in front of it. So if we add everything in front of it, we are adding all of those. How many terms? 100 terms. Yep. Since the counter starts at 1 and ends at 100, we have 100 terms. So 100 terms. So that means S sub 100, right? S sub 100 means the sum of the first 100 terms. And S sub 100 is within 10 to the negative 4 of the sum of the series, which in this case we happen to know. It's one of those rare series that somehow they were able to find the sum of. So we got that. All right, we'll do one more of these. So for this one, I'm looking at the A sub k. A sub k, once again, does not include the switch. And we want to know what is the first k value that satisfies this inequality, that gives us an A sub k that's going to be less than 1 over 10,000. So once again, we cross multiply. We'll have 10,000 less than this. Okay, now we're going to take the cubed root. Let's see how many of you can do that in your head.
Use the calculator.
Wait, what? You're using a calculator?
No, it doesn't come out to a big number.
Yeah, a little bit harder, right? You would have to be a human calculator to be able to get that one. So if we plug it into Desmos or whatever, has anyone plugged it in yet? If you plug it into something like Desmos, we can get the first integer, first integer. So cubed root of 10,000 minus 1. 10, 1, 2, 3, raised to the 1/3 power. Minus 1. Tell me if I'm doing this right.
I think you added 1 too many zeros.
Oh yeah, it looks like 100,000, right? Thank you. Does that look better? So we get that. Let's just take it over here just for grins. So we've got down here. So what is our k value then? The first k value that makes that true is 11. Yeah, so we're going to choose k to be 11. So k will be 11. So k is 11. Let's calculate this. So this one starts at 0. So when we are playing with our expansion here, it should start with a sub 0. And if we plug in a 0 as that initial k value, we see that it starts with a positive. So it's going to be plus, minus, and some dots. And then our k value is 11, so we're going to grab a term before, a term after, and that's going to give us a decent visualization for what's happening. We look over here, and in front of the evens is a plus. So this is going to be plus, minus, plus, minus. When k is 11, we are right here when k is 11. That's less than 10 to the negative 4. So we add everything in front of that. So we want to add those. How many terms is that?
That would be
How many? If we start at 0, 11 terms. 11 terms if we start at 0. 11 terms. So this is S sub 11. That's what S sub 11 means. S sub 11, regardless of whether you start at 0, 1, 2, 5, that means the sum of the first 11 terms. So that's what S sub 11 means. So S sub 11 is within 10 to the negative 4 of whatever the sum of the series is, pi cubed over 32. Look at that. All right. Alternating series. Pretty reasonable to attack the remainder with an alternating series. Again, the more general analysis of an alternating series or of a series remainder is way more complicated. But this gives us the taste of it and the concept behind it. Okay, so we have been talking about alternating series all day. We're going to change our perspective a tiny bit. And when you have a series that has negatives in it, it could be alternating. And if it is, you do what we just did. But if it has negatives that are not separated by pluses all the way through, if it's not alternating, they're just minuses in random places. It could be minus, 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 then plus, plus, minus, just no pattern. So we just have some minuses in there. This also holds for alternating series. Let me just say, to create a series that has a weird pattern of minuses is very hard. It's easy to create where it alternates. Right? We have that minus 1 to the k or minus 1 to the k plus 1. It's going to alternate. But to create a series where the terms are like 3 negatives and then 2 positives and then 3 negatives, you'd have to do some piecewise defined magic or some crazy function. So that'd be very hard to create. But if we have a series that does have some minuses in it, could be alternating, might not be, it might just have minuses, what we can do is talk about 2 types of convergence. So if our series has minuses, there's going to be 2 options. The convergence can be absolute. The convergence can be conditional, if it converges. So the idea then is this. If we have our series that could have some minuses, but we force everything to be non-negative, force everything to be positive, so we take absolute values. So if the series of absolute values converges, then the original series, the one without the absolute values, we say it converges absolutely. Okay. If the series of absolute values diverges, but the series without the absolute value converges, then we say that that convergence is conditional. And so the classic example is the harmonic. So let's look at the harmonic. Does the harmonic converge or diverge? So that's going to diverge. But we just saw that the alternating harmonic converges. So the alternating harmonic converges. And so would the alternating harmonic converge conditionally or converge absolutely? What do you think? Absolute or conditional? Conditional. It's going to be conditional because the absolute values diverge. And when you take the absolute value of the alternating harmonic, you get the harmonic, and that diverges. So in other words, you need, that convergence right here needs the minuses. It's conditional on having minuses in there so that it doesn't blow up to infinity. So this up here diverges. This is regular convergence right there with the alternating series test. And we are going to classify this convergence as conditional. So it's conditional because the series of absolute values diverges. Okay. Now there's a theorem here that we'll use a little bit, but not a ton, that says if the series of absolute values converges, then the series without the absolute values must also converge. Right? So that's saying if you have a series of all positive numbers that converges, if you put in some minuses, it still must converge. Right? If it's all positive and it converges, if you throw in some minuses, that's like letting some of the air out of the balloon, it's still going to converge. So if something converges absolutely, it converges regularly. So if you have some minuses in there, it's got to still converge. All right, so we've got a series that has some negative terms in it. If it's convergent, it can be absolutely convergent or conditionally convergent. And if it diverges, it diverges. There's no such thing as conditional divergence or absolute divergence. It just diverges. So let's look at an example. So we've got that series right there, alternating series. Let's first figure out if this series converges or diverges. If it diverges, there's no point even talking about types of conditional convergence or absolute convergence, types of convergence. So let's first analyze whether this series just converges or not. It's alternating, so which test do we use? Alternating series test. If you have an alternating series, you use the alternating series test. And step one for the alternating series test is to take the limit as k goes to infinity of a sub k, which is everything inside the summation except for the switch. So we have the limit of 1 over k to the 2/3. K raised to any fractional power looks like it's going to infinity, like one of these bird wings, but if it's in the denominator, it makes the fractions go to 0. So this limit will be 0. So that first step checks. Then we go to step 2, and we would like to show that the series has terms that are decreasing. So as we go further out in the tail, the terms are getting smaller, smaller, and smaller. Well, it should be pretty obvious that it's true, because all the k's are in the switch is ignored. All the k's are in the denominator, so if k increases, the denominator increases, which means the fraction decreases. But we have to show it. So that's what we're trying to show. We're going to cross multiply. Cross multiply is going to give us this. All the k's are positive, so we can raise both sides to whatever we want. In particular, we could raise both sides to the 3/2 power and basically ditch the powers. So we have that. Subtract the k's. We end up with an inequality that we can solve by inspection. So now we have both step 1 and step 2 checked. Therefore, the series is going to converge. So the series converges by alternating series test. Now we classify the convergence. So we know it converges. Now we want to say, does it converge absolutely or does it converge conditionally? So now, once we have this convergence, now we're going to consider the series of absolute values. So we're going to consider the series 1 over k to the 2/3. And we have to decide whether that converges or diverges. What kind of series is that? P series. The way you indicate that you know it's a P series is that you identify what P is. P is 2/3. And now we have to remember the conclusion for the P series. That's less than 1, which means divergence. So this is less than 1, and a lot of times the book will write it as less than or equal to 1, because equal to 1 also diverges. Right? If it's equal to 1, it's the harmonic which diverges. So p is less than or equal to 1, and that tells us divergence. So what type of convergence is that? Conditional, exactly. So this is conditional convergence because of the divergence right here. So that tells us that we have conditional convergence. So first step is to figure out if the series converges in the sort of way it's presented. And if it does, then we classify it by looking at the absolute values. So let's take a look at this series. What kind of series is this? Geometric. Yep, the k is on the outside. It's the power. So it's a geometric series. How do we indicate that it's geometric? We identify r. So r is equal to -1/3. And when we're analyzing a geometric series, we actually consider its absolute value. So this tells us that the absolute value of r is equal to 1/3. And now we're going to compare that to 1. That's less than 1. And what is our conclusion when we have less than 1? Converge, right? Yeah, is that what you said? Yeah? Okay. Less than 1 converge for geometric series, greater than 1 converge for a p-series. So we've got that balance there. We've got to make sure we're on the right side of 1. All right, so this means converge. So we have a convergent series. So now that series converges. It's a geometric series. I might just put GS here just as a reminder. If you write R, that's how you indicate that you know that it's geometric, but we'll just be extra thorough. So now we want to classify this convergence. This convergence, we know it converges in a normal fashion. Now let's consider the series of absolute values. So we're going to consider this series where all we do is ditch the switch. So now we have that. And you don't need to put the k equals 1 to infinity. It doesn't matter. It doesn't matter where the series starts, right? Because we have had a theorem that said you can chop off the first finite number of terms and it does not affect convergence or divergence of the series. So it doesn't really matter if you put it or not put it. You don't have to put it there. If you want to, we can. Doesn't matter though. Okay, so what kind of series is that? Still a geometric series. So this series right here has an r value of 1/3, and our conclusion is identical, which is less than 1, so therefore this series converges. So if the series of absolute values converges, what do we conclude about this here? Absolutely convergent, yeah. So that's going to be absolutely convergent. If the series of absolute values converges, then the series absolutely converges. Beauty. All right, here's a brutally hard one. Okay, it's going to take us a little thinking. It's also going to take us a little space in here. Let's move you down here. Learn from experience that that's not enough space. Okay. When we look at an alternating series, we perform the alternating series test to analyze it. Okay, that part is going to be hard when we get to step 2, showing that this is a decreasing sequence of terms. It's going to be hard because of that square root thing. And when you have k plus 1 to the 6th power, to actually do the math, you'd have to expand it, k plus 1 to the 6th, which is a nightmare. So we're going to use a slightly different technique here. We're going to jump back to Calc 1, and we know that a function, and the sequence is a function. The sequence is a function. It's just a discrete function instead of a continuous function. What do we know about functions and their derivatives? If we take the derivative of a function and that derivative is always negative, what does it tell us about the function? It's decreasing. So that is an alternative way to show that a sub k plus 1 is smaller than a sub k. You could take the derivative of the function and show that it's always negative. It's an alternative way. It's usually more work. But when you can't use the regular a sub k plus 1 smaller than a sub k, it's a viable method. So first, let's do step 1. So step 1, it's alternating, so we're going to use the alternating series test. So step 1 of the alternating series test just says take the limit as k goes to infinity. So step 1, limit as k goes to infinity of a sub k, which is everything but the switch. So we have that. Now to evaluate this limit, there's a little bit of work to actually evaluate the limit. The technique that you should have learned in Calc 1, if you have a square root in only one piece of the fraction, the idea is to introduce a square root in the other piece of the fraction, and then combine the two, and then shove the limit to the inside. Because the limit can pass through continuous functions. The square root function is continuous, so it can jump to the inside. So what we have to do then is change this numerator to the square root of k to the 4th. And then we have two square roots, so we can combine them into one square root. And we can move the limit to the inside so that we have this. And then, I don't know what techniques you usually use. There's 3 techniques to evaluate that limit inside. You can use the college algebra technique, where you're just sort of thinking about limits at infinity or asymptotes, horizontal asymptotes. You can use L'Hopital's rule. You'd have to differentiate 4 times, though. What we often do is just divide by the highest power of k. Sometimes you divide by the highest power of k in the numerator. It doesn't really matter. There's a whole bunch of ways to do it. What do you want to do? Divide. Let's divide by what? What do you want to divide by? I don't care. K to the 4th, k to the 6th. Take your pick. Doesn't really matter. One of them will work. They both will work.
K to the 6th.
K to the 6th. Okay. So then when we divide by k to the 6th in the numerator, we're going to end up with 1 over k squared. That's what that says right there, 1 over k squared. Do you agree with that? Bless you. If you divide everything by k to the 6th, that's what you would get. So we can then start evaluating here. And the limit of the numerator is 0. The limit of the denominator is 1 plus 0. 0 divided by 1 is 0. So this limit is 0, so that first step checks. Okay? All right, now the pain in the neck part. So we want to show that that thing is decreasing. Do you agree with this statement? And let me just put a little context here. If we are going to use the first derivative test, we have to differentiate this function. And it's got a square root in the denominator. That's a pitta. That's a pain in the butt to differentiate this with the quotient rule with a square root built in. So there's a clever way to get around that. And that is this. If you square this function, you would get rid of the square root. And it is true, maybe it's not obvious, that if the square of a function is decreasing, the function without the square is also decreasing. If the square of a function is decreasing, you can take away the square, and that will still be decreasing. That's a theorem. So what we could do is say, hey, let's define this function to be the square of this. And I'm going to use x's because we're going to take a derivative, and generally k means discrete and x means continuous. So I'm going to square the whole thing. Square the top, square the bottom, and we get that. So that is the square of this function. And the theorem says, hey, if the square of the function decreases, the function must also be decreasing. All right, so let's find the derivative here. So the derivative, we have a quotient. So we use the quotient rule. At least we're using the quotient rule without an absolute value. So whatever your acronym or whatever it's called is to do the derivative, low d high minus high d low, whatever one you use, divided by the denominator squared, low squared. So we've got that. Simplify this a little bit. Let's see if we can combine like terms in the top. So we're going to have 4x to the 9 plus 4x cubed, and then minus 6x to the 9. And then down below, we just have that same thing. Do a little bit more simplification, and it looks like we end up with minus 2x to the 9 plus 4x to the 3, all divided by same thing, x to the 6 plus 1, quantity squared. So that's where we're at. So now we have to decide, is this always negative? Do you agree that the denominator is positive? Yeah, that's positive. So that's not going to affect the sign of the fraction. So we just, whatever the sign of the numerator is, that's going to be the sign of the fraction. Well, we know that x to the 9th dominates x to the 3. So this term is going to dominate, maybe not in the first few terms, but once you get to where the two curves cross each other, the 2x to the 9 and the 4x cubed, as soon as you get past where they cross, this function here is going to dominate, and it's always negative. So this is going to be less than 0. And a lot of times what I'll just say is eventually. Because it doesn't matter, again, what happens for the first finite number of terms here. It does not matter. When we talk about the convergence of a series, the tail is what matters. If you have a bunch of terms in front that are doing whatever they're doing, it does not affect convergence at all. Right? What matters is when you get out past the leading terms. And so maybe this isn't true if you plug in x equals 1, but as soon as you get to 2, it's true. So this is true when x is greater than or equal to 2 for sure. So as long as it's eventually true for the tail, that's fine. You could chop off the first 100 terms, doesn't matter. As long as it's eventually true for the tail. Okay, so our conclusion here is, therefore, we have a decreasing function. Decreasing is what we need. So this means that step 2 checks with the alternating series test. We have that, that checks. So we have our conclusion here. So therefore, we have that this converges. So we have that this series converges with the alternating series test. Does it converge absolutely, or does it converge conditionally? That's our next step. We're going to need more space. So to decide the classification of convergence, we go to the series of absolute values. So we're going to consider the series of absolute values. So we're going to consider the series. And again, you don't have to put the k equals 1 to infinity. It's not going to matter. So we consider this. And we have to analyze how that series, whether that series converges or diverges. So if we go to that thing I have put at the very end of the end of chapter 10, we don't have, that series there is not one of these special series. It's not geometric. It's not telescoping. It's not a P series. It's not an alternating series. It's all positive now. So those are out. It looks like a total nightmare to integrate. There's a square root in it in the denominator. Maybe you can do integration by parts. We haven't done these two tests yet. These are chapter 10, section 7. How about this last thing? Comparison test. So the comparison test, when all these things ahead of it aren't going to help, the comparison test is a very good test. So when we look at that, do you know what you would compare it to? Any ideas? So we're going to think of this as A sub k. So A sub k is always the series that you're analyzing. A for analyze. It's the one you want to know. What would your B sub k be? Bless you. So to find your B sub k, normally what we do would be to eliminate anything that appears to be insignificant. Adding a 1 is insignificant. So our B sub k, our first choice would be to ditch that little addition by 1 and go with that. And then simplify and see what it simplifies to. All right, well, the square root of k to the 6 is k cubed. That reduces to 1 over k. So that is our comparison series. That's the one that we know. We know what it does. So this comparison series is the harmonic. This has a p-value of 1, which is harmonic. And does that mean converge or diverge? That means diverge. So our suspicion is that the A sub k series also diverges. And we took away this little insignificant piece, and we got a divergent series. So of course, the series are going to behave similarly. So we suspect that the A sub k series diverges. All right. Now, when you go to a comparison test, there are two choices. There is the direct comparison, and then there is the limit comparison. The direct comparison uses a very basic principle. If you have a divergent series as your comparison, bigger than diverging will diverge. So if you have a series that's diverging, so the partial sums are going towards infinity, and then you have another series that's bigger than it, it must also diverge. So the first principle is that bigger than diverging diverges. The second principle is that if you have a convergent sequence of partial sums, and you have a series smaller than it, smaller than converging will converge. So smaller than converging converges, bigger than diverging diverges. Our comparison series diverges, so we would love to be able to show that the A sub k's are bigger than the B sub k's, because then they'll diverge. The problem is that we are not going to be able to show that inequality is true here. If you look at this form of B sub k and this form of A sub k, this denominator is bigger, right? This has the plus 1 inside, so bigger denominator means smaller fraction. So we're not going to be able to use the DCT. So the DCT will be inconclusive. And when the DCT is inconclusive, you go to the limit comparison test. So now we're going to go to the limit comparison test. So DCT is inconclusive, so we're going to go to the limit comparison test. So that's where we go. We're going to take the limit as k goes to infinity of the ratio A sub k divided by B sub k. So the limit as k goes to infinity, A sub k is the one we're analyzing. So it's this one. We are dividing by b sub k, which means multiply by the reciprocal, and evaluate that limit. So this limit evaluates, let's see, we have k to the 3 in the numerator, and in the denominator we have k to the 6 plus 1 inside that square root. We just did something like this a minute ago. If you have a square root in one part of the fraction, force the other part of the fraction to also have a square root, combine the two, and then push the limit inside.
Since we're evaluating k to infinity, couldn't we also just drop the constant of 1 since that becomes insignificant?
Yes.
And then just evaluate that square root as k to the third, simplify that into 1 over k.
And that will also work. So when we look at limits in this form, we can absolutely do with that. So the concept that you're talking about is that inside that square root, the dominant term is k to the 6. And that polynomial that's in the inside is completely determined by that leading term. So 100% we could do that also, for sure. And I tend to do this with the square root technique because we need it for other things. So it's a good technique just to have in the bag. But what you just described is absolutely legitimate. You could just ditch that 1. And so we've got this if we use that square root property. And then we're going to divide everything through by k to the 6. Or you could use the college algebra technique and say, oh, the ratio of coefficients is 1. Both have the same power. So you could do that. So we end up with square root of the limit inside here. We get 1 over 1 plus 1 over k to the 6. That's all going to be 1. Because 1 over k to the 6 goes to 0. So either technique we use, we would get 1. Now we have to go. The hardest part about Chapter 10 is remembering how you conclude each of these tests or each of these special series. So we've had less than 1 stuff happens. We've had greater than 1 stuff happens. Now this one has an equal to 1. For the limit comparison test, what does that tell us? So it tells us if the limit of this ratio is a positive real number, and I indicated that by saying this. This math notation here, epsilon means element, E for element. This means positive reals. If you just have the double barred R, it's all reals. If you put a little plus, it's the positive reals. This also means you could write 0 less than 1 less than infinity. That's another way to say it. So it's a positive real. Then both series do the same thing. So if you get a limit for that ratio, it means that the two series are attached and they're behaving in parallel. So either they're both going to diverge or they're both going to converge. So this tells us that both series, so therefore both series, since our b sub k series diverges, we have that both are going to diverge. Okay? So both diverge. So now we have to sort of remember what we were doing originally. So we have this alternating series. We calculated that that alternating series converged. And then when we went to the series of absolute values, we got diverged. So now we can classify this convergence as conditional. So after all that. So this means that, therefore, we have conditional convergence for the original series. Conditional convergence. So that's a long one. That's about as bad as they get. That's uses a lot of different things. Okay, so let's talk about the next one here. The next one's a little bit easier, maybe a lot easier actually. It's an alternating series. So why don't you all try to show that this converges using the alternating series test. So you do that part. So AST, it's an alternating series, so we're going to go with the AST. So show step 1 and step 2 here. I'll be right back. I'm going to run to the restroom. How's it coming? Pretty good? Class is so quiet. Are you guys always so quiet? Are all the obnoxious people in my Calc 2 class? Yeah. All right, so we're going to take the limit as k goes to infinity. My class is actually great. Very not obnoxious. All right, that limit is 0, so that checks. Right, denominators go into infinity, fractions go to 0. Now we have to do the decreasing part, so we would like to show that as we go further out in the series, the terms are getting smaller, so it's decreasing. So we have our a sub k is 1 over ln of k. Don't know, is this true? So we've got that. We're going to crisscross, multiply here. So we want to know whether this is true or not. And everything is positive, so we don't have any funny business going on. We can exponentiate both sides. When we exponentiate both sides and then subtract k, we get our numerical inequality that we can solve by inspection. And this is true. So this is true. So that checks. So our conclusion is that, therefore, we have regular old convergence. So we have an alternating series that converges. Now we want to classify that alternating series convergence. Is it absolute? Is it conditional? That's what we want to know. So we consider the series of absolute values. So we're going to consider, I think I spelled that right. My wife is an English teacher. I should know how to spell consider. So we have that. And you probably already did this one. Do you think converge or diverge? Diverge. If we think about our threshold series, the harmonic p series, right? The harmonic is 1 over k, And those terms go to 0, but they go to 0 too slowly for convergence. Doesn't 1 over natural log of k go to 0 even slower? Because natural log goes to infinity slower than k goes to infinity. So that means that the fractions are going to go to 0 even slower. So our hunch should be that it diverges. And we can show that with a comparison test. If we choose b sub k to be the harmonic, so the series that we're looking at is 1 over k as our comparison series. This one has p equals 1, which is the harmonic, which diverges. Then we would like to show, we're going to use that principle that we talked about a minute ago, bigger than diverging diverges, smaller than converging converges. So if we've got a series that diverges, so the partial sums are going off to infinity, and our series is bigger than it, it must also diverge. So let's check. Can we show that, so a sub k is the series we're analyzing, b sub k is the series we picked as our comparison. So can we show that? If we can show that, then we've shown that that series diverges. All right, can we show it? Let's see. A sub k, that's the series we're analyzing. So 1 over ln k. Is that bigger than 1 over k? We don't know. We'll put a question mark. Cross multiply. And we're here. And now we're going to look at a graph. You can claim that that's true. Back in Calc 1, maybe you did it in Calc 1, I don't know, it depends. So here is a picture of y equals x. Here is a picture of y equals absolute value, natural log of x. There's an asymptote there. And we can see that x is bigger than ln x, aka k is bigger than ln k. Right, so all across the board. Now if you wanted to actually prove that that's true and not just say true by inspection of the graphs, you would take a look at this place right here at 1. That's where these two functions are closest. And you can build the function that measures the difference between the two. And here you can find the value of 1, the value of 0. So this function's bigger there for sure. And then as you define the difference function, let's say it's f minus g, you can show that f minus g is an increasing function. And if f minus g is an increasing function, then this function's always going to be bigger than that function. So you can prove it with Calc 1. So what is our conclusion then? This series right here, converge or diverge? So our b sub k series diverge, so this a sub k series also diverges? Correct? So this series diverges. All right. And now our big conclusion, we go all the way back up here. This convergence is conditional. Exactly. So this will be conditional convergence. So this tells us down here that we have conditional convergence. Correct. All right, so that's all of alternating series. So we'll talk a tiny bit about the next section, unless someone has a question on any of these steps for alternating series. Alternating series. Very systematic. This is probably one of the easier sections because you've got rules that are very easy to kind of remember and apply. So it's a little easier than some of the more abstract sections. Let's take a little gander at the ratio test. So of all the tests that you're going to come up with, there's 10 tests / special series. Of all of them, the ratio test is the one I would say is the most important going forward. Next week, you're going to be going to chapter 11. And in chapter 11, you're going to be studying power series. So up until this moment, you've been studying series that have numbers in them. Right? You've got an infinite series of numbers. And you're deciding whether those series converge or diverge. In chapter 11, when you get to something called a power series, you're going to have an infinite series of powers of x. So those are going to be functions, and every x value that you plug in is going to generate an infinite series of numbers. All right, so power series is an infinite collection of infinite series. Some of the x's will cause convergence. Some of the x's will cause divergence. The ratio test is going to be pivotal in dealing with these power series. So that's why the ratio test is going to be super important, because it's the most persistent of all the tests. It's the one that you're going to use a lot in the next chapter. So let's take a look at the ratio test and at least sort of get a concept of what it means. So we are going to form something that looks a lot like what we just did. It looks a lot like the limit comparison test, where you look at the a sub k over the b sub k. It looks a lot like that. So what we're going to do is form, there is a typo in this. I fixed it down here, but I forgot to fix it up here. This should be a sub k plus 1 in the numerator and a sub k in the denominator. It's the ratio of consecutive terms. So when we think about the ratio of consecutive terms, we're going down through the series. We're going to take the a sub k plus 1 and put it over the a sub k. So we're putting the smaller one over the bigger one. Right? That ratio, the terms are going towards 0. So a sub k plus 1 over a sub k should be a proper fraction. It should be smaller in the numerator than the denominator. So we form that ratio. And then take a look at these conclusions. This should remind you of something. The geometric series. Right? The geometric series has convergence, and they use an R, just like in the geometric series. If R is less than 1, you have convergence. Greater than 1, you have divergence. Here, if you get R equals 1, you just have to try another test. It's inconclusive. All right, so the next question is, well, if they're using an R, and that's what we use in the geometric series, there's probably, and the conclusions are the same, there must be a reason. So let's take a look at this outline of the proof. So when you form this limit, what you really mean is that out in the tail of the series, this ratio is about equal to R. Right? If the limit of the ratio is R, that means when you go way out in the series, that ratio is about R. If you look at a sub k plus 1 over a sub k. All right, so let's go out to the tail then. So if we go out to the tail, so we're saying that that thing is approximately equal to R. So if we multiply both sides by absolute value of a sub k, we get this. So out in the tail, we have our a sub k. Next term is a sub k plus 1. Well, a sub k plus 1 is just R times a sub k. And that whole concept bootstraps. The next term is about R times the prior term. The next term is about R times the prior term. What kind of series is that? When you have a constant multiplier? Geometric, right? That's what geometric series are. You have a common multiplier that you use to get to the subsequent term. And so if that is behaving like a geometric series, that's why the conclusions are what they are. And that's not a formal proof, but that gives you the concept of why the summary of the ratio test is going to be identical to the summary of the geometric series. So that is why. Let's do one example, and then we'll call it a day. Let's take a look at this top one. Now, one thing I want to point out is that with the ratio test, you take absolute values. So you're taking the absolute value of a sub k plus 1 over a sub k. So when we do that here, we're going to say the limit, as k goes to infinity, of a sub k plus 1 over a sub k absolute value. The absolute value is just going to ditch that -1 piece. So we are going to have the limit, bless you, of 2 to the k plus 1. The absolute value takes away that. And then down here, we're going to have k plus 1 factorial. So there's a sub k plus 1 in absolute value. A sub k, same thing. We take the absolute value. The minus is gone. We're going to have k factorial divided by 2 to the k. So that is our ratio. How many 2's are we left with, and where are they?
Two, greater.
1, 2 up top, right? There's one extra 2. It's going to be in the top. And how does k factorial over k plus 1 factorial simplify? K plus 1. That limit is 2 in the top. The limit of the numerator is 2. The limit of the denominator is infinity. So 2 divided by infinity will be 0. And then geometric series. This is less than 1. Therefore, convergence. So therefore, converge. Now, one thing you could say, this series does have some negatives. And we took an absolute value. So we could actually classify this convergence as absolute, because we took absolute values. So this converges absolutely. So the ratio test, is actually detecting an absolute convergence if there's minuses in there. And so if it converges absolutely, it converges regularly also. All right, there's a ratio test introduction. Cody will be back on Thursday and finish off the ratio test and the root test. And once you finish the ratio and the root test, then you have all 10 of your tests done. It feels like you're juggling a lot of balls. All right, live long and prosper.